describe the Hyper-Kamiokande experiment, give the current status of where we are, and talk about the physics that we would like to do. And I'm meant to start off by giving a bit of background so that we know where on this road that we are trying to follow, that we start from. So for those who don't know, neutrino oscillations are now well-established experimental phenomena, and they're always easier to think about with just two neutrino flavors. So if you can imagine that we have a nu mu beam turning into nu e, then while you might expect that the neutrinos will just travel from point A to B, it turns out that they will actually change flavor as you travel, and then they will change back. And so you get this oscillatory behavior between the two flavors. So although the total number of neutrinos is conserved, the flavor, it isn't, and we get this large-scale quantum mechanical oscillation, which has two free parameters. The first of which is the amplitude, which we can codify for what we call a mixing angle, and the other of which is the wavelength, which is essentially given to us by delta m squared, which is the difference in the mass squared between the neutrino states. And this arises due to the mixing between the flavor eigenstates, where the flavor is defined by the weak interaction and the charged electron that you get out the other end, and the mass eigenstates, which are the states that essentially travel through space. So because this is a new phenomena, that means that we can compare it to the quark sector, where we also see mixing. However, this mixing is very much larger, which is initially flew against what people would expect. And the other thing that's really key here, and is going to be the focus of what I'm going to talk about, is that once you add the third generation of neutrino to this, you introduce a new place where CP violation can live. And if you're interested in questions such as why are we here from the Big Bang, where you would expect equal amounts of matter and antimatter to be created, well, we know we need CP violation as one of the Sakharov conditions, and a new place for CP violation can give us a new place to search for where we could actually satisfy that. So once we move to three neutrinos, we can see a characteristic mixing matrix. This is a unitary, a 3 by 3 unitary matrix, and by the various conditions, there are 4 free parameters. You can define this in various ways. In the neutrinos, we do it differently than the quark sector. We use 3 mixing angles, which are very much reflected in the experiments that we do. And the 4th parameter is a CP violating phase, delta CP, which always lives in combination with a sign of theta 1,3. And that explains why we were so interested to measure theta 1,3 about a decade ago when we didn't know its size, because if it was 0, then even if the delta CP was kind of maximal, there would be no impact on any observables. And that leaves us in a position where we end up with a set of unknowns for neutrino physics. These unknowns are the mass hierarchy. We don't know whether M1 or M3 is the lightest neutrino. We do know that M1 is lighter than M2, but we don't know whether it's kind of a normal ordering, such as M1, M2 to M3, such as we see in all the other, in all the other fermions, or whether or not M3 is actually the lightest, and we end up with an inverted ordering. We don't know what the CP violating phase delta is, and we don't know if CP is conserved or not, which would be given to us by sign of delta being 0. We don't know the octant of theta 2,3, or whether it's maximal. The octant basically means, is it bigger than or smaller than 45 degrees? Those questions can all be answered in oscillation experiments. You need other types of experiments to answer the absolute mass scale, the Dirac or Majorana nature of neutrinos. These would be things like Plus, maybe I'll talk about that. And of course, there are still these open questions of, are there sterile neutrinos, for which you need different baselines than the ones that we're going to use in Hyper-K. And what we're going to do to search for CP violation is to search for the appearance of electron neutrinos in a muon neutrino beam, which is given to us by this horrendous looking formula on the screen. However, it's relatively straightforward to break down. The phi's are all oscillatory pieces, so they tell us the baseline we need to search at. In the green box, we have the solar mixing baseline. But we can basically ignore that for the experiments that we're going to do. We're going to look at the baseline that was given to us by atmospheric neutrinos. And we see a leading order term, which depends on sign of theta 1,3, and then two correction terms that depend on delta. One of which is even, so is the same for neutrinos and antineutrinos, and it distorts the appearance probability spectrum. But the other of which is odd, it depends on the sign of delta, and that tells us it's going to be different if we have neutrinos or antineutrinos. We basically will pick up a minus sign when we go to antineutrinos. And finally, we have a matter effect term, which depends on the distance and therefore increases with increasing energy, assuming that you fix yourself at the oscillation maximum, but also now depends on sign of this delta m squared L over E rather than sine squared. So it tells us also about the hierarchy, because it's no longer going to just be simply something that goes away, and it's going to be a dependence on whether M1 or M3 is the lightest. And if we want to make these measurements, there are certain things that we need to do in order to basically pull out this probability. We need to know the distance. That's easy because we've built our accelerator in one place and our detector in another. We need to know the neutrino flavor. That's slightly harder. We need to be able to distinguish between muons and electrons. We need to know the neutrino energy. That's actually quite difficult because we don't observe the neutrino directly. We observe the decay with the products of the interaction, so the leptons and maybe pions as well, and we need to know the rate, so we also need to know the cross sections. But the neutrino energy is the key, and depending on where your distance is and therefore the energy of the neutrinos that you're going to select, that will tell you about the detector technology choice that you need to make. So if we look at the neutrino cross sections as a function of neutrino energy, you can see that below about 1 GeV, then we're dominated by these quasi-elastic interactions, and we can reconstruct the neutrino energy from the event kinematics. The neutrino energy is basically a function of the lepton momentum and direction with respect to the beam. There are corrections and uncertainties to this that become important for future experiments, such as 2p2h interactions, where the neutrino doesn't interact with a single nucleon, instead it interacts with a correlated pair. But in general, you're going to want to, we need to measure just the lepton in order to do the experiment. If we go to higher energies, first above a GeV, we first of all get resonances, and then we just, if we go even higher, we just be dominated by deep inelastic scattering, where the neutrino is a scattering of the quarks rather than nucleons. And at that point, the primary lepton doesn't really tell us everything we need to know. We're going to have to measure the neutrino energy calorimetrically, so by measuring the energy of all the particles that are emitted in the final state. And this knowledge is what tells us about what we need. So if our baseline is such that our neutrino energy is less than a GeV, a detector like water Cherenkov will work because that can measure the primary lepton. If you go to higher energy, longer distances, so higher energies like June, then that doesn't work anymore. We need to measure everything. So you need the detector technology like liquid argon. And so this really tells us the distinction between Hyper-K and June. Hyper-K is a shorter baseline. We can use water Cherenkov. Water Cherenkov allows us to go to more mass. Whereas for June, they have to use liquid argon because they have to reconstruct all the particles in the final state. So that's the state of play for kind of building up a long baseline experiment. But it's important to know where we are at the moment. So here are the latest Tdk results. So here is the data sets. So we have anti-neutrino mode here at the top and neutrino mode here at the bottom, where we've measured nu mu, nu e, and in neutrino mode, we have this CC1 pi channel where we look for a single decay electron as well. You can see the effect of the oscillations, this dip here in the nu mu. This is actually much more pronounced than it looks because we haven't shown the unoscillated spectrum in the predictions. And the beam peak is right where the suppression is. So this is a very, very large effect. And then we can also see the nu e appearance in both neutrino and anti-neutrino modes as well. And what we can do is then turn these into the results. The first way of thinking about this is to just think about what the appearance probability is. And here we've cast this into the number of candidates we see in neutrino and anti-neutrino mode, respectively. What we get are then a series of predictions for what this would be based upon the inputs. So if we go around one of these loops, we're basically tracking delta Cp, and then the mass hierarchy splits these two loops from each other. And you can see that Tdk results favor a large value of delta CP and the normal hierarchy, although they certainly don't exclude the inverted hierarchy either. And you can then see this appear in our delta chi-squared plot. So you can see the Tdk results very much favor a delta CP of around minus pi by 2. And large chunks of this parameter space in the plus pi by 2 regime are excluded at more than 3 sigma. And we're getting close to being able to make statements here about 3 sigma about the CP conserving points at 0 and pi. You can see this as well if we expand this out and look at the phase space that's opened up in delta CP and sine squared theta 1,3. You can see how this region in the middle is being excluded. When we introduce the constraints on theta 1,3 from the reactor experiments, we kind of blow this region up, so you can see that the scales are different here, and we've zoomed in, and you can see this gap really appearing. So the reactor experiment constraints on theta 1,3 are further improving what we're actually understanding, and those are included in this plot down here. At longer baselines, we have the NOVA experiment, and you can see over here the real impact of going to longer baselines. In NOVA, the hierarchies are much more separated than they are in Tdk, and these loops are also a little bit wider as well. But this is the same plot we were looking at for Tdk, except for the fact that we're now looking at it for NOVA, and their best fit point, their measurement is slap bang in the middle, so they can't see the difference between the hierarchies at this point. You can see why in general they would be better at doing that. And you can see here their exclusion plots. And just for reference, I put the exclusion of theta 2,3 and delta m squared 2,3 here as well. You can see that both Tdk and NOVA, which is the red in Tdk and the black is NOVA, are very much in agreement with still maximal mixing. But the interesting thing is that the NOVA exclusion and the Tdk exclusions are kind of a little bit in competition with each other. So this is something to watch as both experiments collect more data. Whether or not this is real tension or whether this is going to go away is something that's very much key to looking forward. And what does this give us until, say, 2027, which is the date when we expect Hyper-K to begin, is that Tdk and NOVA will continue to run, so we will get increased statistics. However, even putting this tension to one side, we won't get 5 sigma CP. So there's just not possible with the current setups that we have. We won't get enough statistics. We won't push the systematics down sufficiently. So precision measurements are not possible. The mass hierarchy is slightly different. I think it's perfectly feasible. We'll know the mass hierarchy at 3 sigma. Juno will say something about it. Measurements at the South Pole will say something about it. And the combination of Tdk and NOVA might say something about it as well, all of which can kind of give us an idea at the 3 sigma level whether or not we're in the normal or inverted hierarchy. So that sets the scene, and now I want to move into describing Hyper-Kamiokande itself. So Hyper-Kamiokande was approved in Japan last February. You can see here the signing of the MOU between the KEK and the University of Tokyo. The University of Tokyo through ICIR will run the big fire detector, and KEK run the accelerator at JPARC and the near detectors. And you can see that construction has already started. Here is a photograph of the entrance yard. You can see the work being done to get this ready. The entrance tunnel is over here, and the entrance tunnel is being worked on, and various bores have been taken and such. And we now actually have a photograph, although I'm not allowed to show it, of the center of the cavern where Hyper-K ultimately will be. And construction is underway, and we will begin taking data in 27, hence the previous slide mentioning 27. And here is the collaboration. So we had a collaboration meeting last month. So rather than show the usual people gathered on the steps at the University of Tokyo, we took a photograph of various people collected together on Zoom. I think this was right at the end. So particularly in Japan, it was quite late and a lot of people would have to leave. But you can see here, the collaboration is growing. We're currently formally in 18 countries of 82 institutes on 4 continents. With almost 400 members, and this is growing, and Morocco is about to join, which will give us a 5th continent to add to our list. So this is a growing collaboration now. Is now that we're really moving forward and pushing forward with construction and thinking about what physics we can get out in even more detail. So Hyper-Kamiokande is a step up on Super-K, order of magnitude larger for measurements of neutrinos and proton decay. We have bigger detector with better photosensors, so we will do, be able to do more. We will more beam power and upgraded near defectors to get more statistics even then in the beam and drive our systematics down to make this CP violation measurement, kind of make the categoric measurements there, do the mass hierarchy, do the octant, have unprecedented supernova sensitivity, measure solar neutrinos, and measure proton decay. And I'll cover each of these topics as I go through this seminar. You can see here kind of the progression. Kamiokande, which ran from 83 to 96, was a kiloton scale. And, the measured supernova 1987A measured the atmospheric anomaly and the solar neutrinos and really confirmed, the suppression there. Super-Kamiokande, which is 50 kilotons, is now running and has been running since 1996 and sets, a number of things, including, the Nobel Prize for discovery of neutrino oscillations through atmospheric neutrinos. And now Hyper-Kamiokande plans to go an order of magnitude bigger again to explore new physics. And the detector itself, you can see here, would have a fiducial volume of almost 200 kilotons. So this is about 8.5 times larger than Super-K, where the fiducial volume is 22.5. You can see the size of the cavern. It's a very, very large underground cavern. The water depth is 71 meters. And with the dome over the top, we reach almost 80 meters in height. And this cavern will be extremely large with the latest in the technology for the very large PMTs providing the readout. It's a water Cherenkov detector. So this exploits Cherenkov light. Cherenkov light is essentially the optical equivalent of a sonic boom. We have a charged particle traveling faster than the speed of light in the water. Then you get a buildup and the reinforcement of the light in a particular angle from interference, and this gives you a cone of light that is emitted from the particle, and the angle of the cone depends on the speed of the particle. So if the particle is going just over the speed of light, you'll get a very narrow cone. If it's going essentially at c, then you'll get a cone of about 42 degrees. And as the particle travels through the water, it might get scattered around, so you get multiple cones pointing in different directions. And that's the backbone of the electron to muon separation. You can see here a muon where we have a very sharp ring because the muon doesn't scatter very much. And for the electron, we get a fuzzy ring because the electron scatters a lot. And this allows us to separate electrons and muons at the greater than 99%. And then the amount of light you see in the inferred length of the tracks allows us to do a good job of reconstructing the momentum of the electron or the muon as well. The detector itself will be sited not very far from Super-K, about 8 kilometers to the south, but underneath a different mountain. The beam from JPARC will actually bisect the two detectors. So this is the same off-axis angle as Super-K, but on the other side of the beam. And we'll have an overburden of 650 meters. So this is a bit less than Super-K has, but it still allows us to do all the measurements that we want to do. This detector itself, if you've been to Super-K, you'll know Super-K is located in a tiny village called Mizumi, not actually in Kamioka. Hyper-K is actually much closer to Kamioka itself. So we'll be likely to base a number of things in Kamioka, and we're already doing things there, such as storing PMTs and so on. The photosensors are the central part of the experiment. So we will have 20,000 of these 50 centimeter box and line PMTs. These are much improved photosensors compared to Super-K. So you can see that the transit time spread is reduced, and that's what we need because the transit time spread is what tells us about the position resolution. The charge response is much improved. You can see the vastly greater separation between the 1PE peak and the pedestal, which will allow us to do much better colorimetry. But most importantly, the quantum efficiency is also much improved. You can see that essentially the quantum efficiency is increased by about a factor of 2 over the Super-K, PMTs, and that means that the effective coverage with these 20,000 box and line PMTs is very similar to Super Ks, and will allow us to measure everything we need and do much better because of the mass. There's also discussion to add MPMTs to Hyper-K as well. So this is a development of the optical DOM module idea that is used in things like KM3net and IceCube, where you take a box and you put multiple smaller PMTs in order to provide one unit that provides your readout. These smaller PMTs have concentrators to point them to give angular measurements to these, and that's actually very useful for various bits of physics and calibration. There are 19 of these 3-inch PMTs inside a single DOM, which is also the 50 centimeter size, so the same size as the other PMTs. These are faster, and they give you higher resolution of the measurement of the ring. The downside is there's a smaller photocathode area per unit, so you get fewer photons. So they're very quickly add to the physics you get for high energy, but the rate you get for the low energy physics is a bit less. These will be the photosensor option for IWCD, which I'll describe in a moment. And there will be up to 5,000 of these added to Hyper-K, given that these will be an international contribution, whereas the Japanese are funding the 20,000 box and lines. The exact number of these is yet to be determined, as it depends upon various countries getting the funding to do them. And many other detector systems are under development. So you can see here as we go around the outer detector, which will consist of 3-inch PMTs plus wavelength shifting plates. There will be PMT colors to avoid any catastrophic chain reaction of an implosion. The electronics is planned to be underwater, so as well as developing the electronics, we have to make sure that we can make these watertight boxes to support the electronics and make sure they don't get flooded. We have a mock-up already of the support frame so that we can see how to mount everything, not just the PMTs, but also the electronics boxes, calibration components, the outer detector, and how to fit Tyvek to everything and so on. And we're developing many different parts of the electronic systems. Here's a photograph of the clock system in a test stand. But there are, the HPK readout chips are being developed, and all of these things are moving forward rapidly. Something closer to my heart is the calibration. This is what I'm working on myself. And the idea here is that we have to improve the systematics compared to Super K. So we have a variety of systems from light systems. So here's a multi-headed, multi-shaped light injection system that we're developing in the UK. We will be deploying an electron LINAC, which will be similar but slightly more powerful than the one that we have in Super K, to do calibration of low energy physics alongside using a DT generator to generate nitrogen-16 clouds in the detector. There will be various radioactive sources, such as the californium, nickel, and AMBE source to also do this. We will have many, many samples of higher energy events, such as Michel electrons from stop muons, through-going muons themselves, pions, and so on, in order to calibrate high energy physics. And we have an extensive pre-calibration program planned where we will be fully characterizing many of our PMTs. You can see here the photosensor test facility at Triumph, which measures the PMT timing, charge response, and quantum efficiency as a function of location of across the front face and of photon direction, so that we can have a really good model that we can put into our simulation. The long baseline setup is shown here. So we have the accelerator at JPARC. This will be upgraded towards 1.3 megawatts starting next year, where we upgrade the power supplies to increase the rep rate. And so this all happens as part of Tdk and gets improved through to Hyper-K. Similarly, we have near detectors, the upgraded ND280, again from next year, and also IWCD, as well as the Ingrid detector. And overall, this will allow us to collect statistics at 20 times the rate we currently collect them in Tdk. The near detector itself, the upgraded near detector will look like this. So the region on the left is basically the same as the region that we have now with the FGDs, the TPCs, and the ECALs. However, on the right, we will replace the old pi0 detector with a new system with a scintillator target and time of flight detectors and horizontal TPCs. The old pi0 detector has served its purpose. Essentially, we were worried, of course, about the pi0 background for the theta 1-3 measurement. Theta 1-3 is relatively large. We understand that pi0 background well now, so we replaced that detector with the new part. And what this detector does is this allows us to round out our phase space coverage and basically push down our thresholds and do things better. So one of the issues is, of course, that in Hyper-K, the primary electron can go in any direction. It's obviously favored to go forward, but it doesn't always have to. And in ND280, however, as you can see from here, the neutrino beam comes in from the right, and things that go forward, we reconstruct very well. Things that go sideways, not so much. So with the new sideways TPCs and the better fine-grained detector, we can round out that phase space coverage to cover essentially 4 pi. They also lower the threshold. As you can see, the super FDD, that fine-grained detector there, it consists of these 1 centimeter cubes of scintillator that are read out by fibers in 3 different orientations. And this drops the thresholds to protons. It allows us to do decent tracking inside the detector itself, and also gives us some sensitivity to neutrons. So overall, this is just a much more capable detector than the existing one. And we get better time of flight and allows a great reduction of incoming backgrounds from, there's a better PID in reduction of incoming backgrounds from the time of flight detector, which will again further improve the physics that we can do. So this is due to start in the end of next year. We installed from the beginning of next year. And despite COVID, this is well on track to go in. So we'll actually operate as part of Tdk and then be ready to be picked up as the initial near detector for Hyper-K. In addition to the ND280, there's also the intermediate detector. So this is 1 to 2 kilometers away from the target. And this is a water Cherenkov detector of about 1 kiloton. The primary sensors are these MPMTs. You can see the simulation up there. And this gives us about the same resolution of the rings as we'll get with the box and line PMTs in Hyper-K. But the real trick of this detector is to exploit the off-axis effect even more so than we do now. As you move further off-axis, your average energy of your neutrinos is lowered, and it goes up at those low fluxes and comes down at the high fluxes, at the higher energies. And what that means is that we actually can change and control the neutrino spectrum that we measure with the same beam, if we can change the off-axis angle. So the way that we change the off-axis angle is that we build a deep shaft, and then this detector can move up and down the shaft, essentially by flooding the shaft with water, and then by changing the water level, we change the height of the detector. We can then make measurements of the lepton kinematics as a function of these different spectra, and that allows us to disentangle the spectra of the lepton kinematics and the neutrino energy. And remember, the neutrino energy we're trying to measure from the lepton kinematics. And so this can vastly reduce our systematic uncertainties on our measurement of neutrino energy, which is what we need for this experiment. So the IWCD will use this to really, improve our systematics. We can add gadolinium to get neutron measurements as well and measure neutron production. And the other place where this can win is to measure electron neutrino cross sections. The biggest issue we have in ND280 for electron neutrino cross sections is not the elimination of muons. That actually works very well. It's the elimination of photons. And of course, we're looking at 1% of the beam, so the other 99% can make pions. Those pi zeros give us photons, and those photons can enter our detector. And it's quite hard to tell the difference between a photon coming in and giving you an electron and a neutrino coming in and giving you an electron. So what you need is a self-shielding detector, which is what IWCD gives us. And you can see here how the incoming photons from pi zeros is really very, very small effect in IWCD, whereas in ND280, it's a dominant background, far bigger than the signal. So we can measure these electron neutrino cross sections, and given that the CP appears through new appearance, this allows us to really control our systematics to the level that we would need to. So the oscillations occur, and you can see here what actually happens at the Tdk baseline of 290 kilometers. and with those different factors coming in. So you can see how the appearance probability changes as we change delta and we change the mass hierarchy, and for neutrinos and antineutrinos. And we will essentially be measuring this probability for both of them. What we will need to do, of course, for Tdk only Hyper-K only measurements is also try and measure the mass hierarchy. And for that, we will use atmospheric neutrinos. So for atmospheric neutrinos, the nu E signal is very interesting. You can see for different scenarios how you get actually different oscillation curves appearing as a range, as a function of energy for the atmospheric neutrinos. And for the mass hierarchy, you get this big probability from this resonant effect here around about 5 GeV. But in the inverted hierarchy, this doesn't happen in neutrinos, it happens in the antineutrinos. So this gives us a possibility to actually measure the mass hierarchy with atmospheric neutrinos, provided you can collect enough of them. And ultimately, the combination of these is what gives Hyper-K its best sensitivity alone without external constraints for delta CP. So what we do is we can look at the exclusion of sine delta CP equals 0, i.e. CP conservation, as a function of true delta CP. And you'll always get these characteristic curves, coming up and down when you get maximum sensitivity when you was maximally far away from 0 or pi. And obviously you will never exclude delta CP, sine delta CP equals 0 if it actually does. So we get about 8 sigma exclusion at the Tdk preferred value here, about minus 90 degrees. But we get very good coverage across the board for exclusion of sine delta CP equals 0 with Hyper-K, due to the fact we're collecting so many statistics. So we end up with many thousands of events in both nu E and nu E bar appearance. You can see here how knowledge of the hierarchy improves your sensitivity in this positive region where you get more of the overlap. And so you see the atmospherics coming in and cleaning this up. And then if you input knowledge of the mass hierarchy from somewhere else, you essentially make these curves symmetric. And you can see here how we exclude large fractions of parameter space at 3 and 5 sigma as we run. And then you can see the impact of the systematics. This is applying the systematics as they are in Tdk from the 2018 analysis. And this is shown again here, starting now from 2027 for the exclusion of sine delta CP equals 0. At the top of these curves, we are statistics only. At the bottom, we are the Tdk 2016 systematics, which is, and the nominal systematics are kind of this dotted line here. And you can see how the systematics are important and why we need to do so much better on measuring cross sections and understanding the detector, so we can get more, we can exclude more of parameter space and really, understand and measure CP. You can see here for delta CP equals minus 90, we're getting our 5 sigma relatively quickly anyway. But if we're at 45 degrees, so closer, you can see how important it is to really push those systematics down. So this shows us the prospects of CP violation measurements at Hyper-K, and I think they're really excellent. Very, very sensitive to CP violation for a large range of parameter space. I'm now going to shift gear. I've been speaking about the CP violation measurement for the majority, for the vast majority of the seminar, but I'm going to shift gear and just talk about a few other topics for the last 5-10 minutes. So we measure solar neutrinos as well. We'll be measuring the boron 8 neutrinos and maybe the HEP neutrinos. HEP is a challenging measurement to make, even at the size of Hyper-K, because the flux is so low, but we might be able to say something. However, the more interesting topics that we will be able to say something about are the day-night asymmetry and the upturn. If you look here, this plot shows the solar accepted regions and the CAMLAND accepted regions, and you can see a little bit of tension in the delta M squared. The day-night asymmetry contours of constant day-night asymmetry are shown here. You can see how they measure delta M squared. So if you can measure delta M squared better, through the day-night asymmetry, you can maybe resolve this tension. And you can see here how for various levels of systematics, we will be sensitive to seeing whether this difference is real or not very, very quickly. After 5 or 6 years, we can really start to pin this down and see whether this tension is something to be interested in or whether it will go away. More interestingly, again, is the upturn from the MSW effect. So this is how you transition from the matter-dominated oscillations we see in SNO and in Super-K and so on, to the more vacuumy oscillations we have in the PPs. And this measurement of this upturn can tell us about non-standard interactions and really confirm that we understand the MSW effect. You can see here for Hyper-K, this is the sensitivity to seeing this, this upturn. You need a lot of data, but you also need to push the systematics down and push the threshold down. But we think we can get down to this 3.5 MeV threshold for the solar neutrinos and get the systematics in position, which means that after about 10 years of running, we have a chance to actually observe the upturn at 5 sigma. So there's still some interesting solar neutrino measurements that can be made. Hyper-K is also sensitive to supernova neutrinos. So as I mentioned before, Kamiokande saw supernova in 1987A. They saw 11 events, and there were 8 observed in IMB. However, Hyper-K for a galactic supernova would observe far more than 11 events. And in some cases, it can be tens to hundreds of thousands if it's a nearby star. And this can give us access to a wealth of supernova and neutrino physics. So we definitely want to make sure we can get them. The DAQ is being developed to make sure that none of this data will be lost. What you can see here is, as a function of time, the fluxes of the various different types of neutrino that we would get observed through various different interactions. So electron scattering and absorption of antineutrinos on protons and oxygen. And particularly the electron neutrinos can absorb on oxygen-16. You can see how oscillations changes what we observe. And in particular, with reference to this neutronization peak, you can see how the no oscillation case is changed, that neutronization peak is changed quite dramatically. You can actually see the impact of the hierarchy pretty directly here in what we get. So if we can measure a supernova, we can measure a huge amount of neutrino physics in that. As I said, there's a huge amount of supernova physics you get too. We can look at this in a slightly different way. You can see the impact of theta 1,3 on the shock with the normal and the inverted hierarchy. Again, you can see very, very different spectra. So you can really pull things out. Of course, supernova are rare, and we expect one every 25 or so years in the galaxy. But if you want to increase the number of supernovae that you need, then you can't really increase the number of stars unless you can increase the range. And what Hyper-K does is it actually gives us sensitivity to Andromeda. It's only 10 or so events, but if there's a supernova in Andromeda, we would see the burst signal in Hyper-K, which I think is really exciting. It gives us more than twice as much probability of seeing a supernova just due to the number of stars. The other way of seeing supernovae is to, instead of seeing a burst, is to look for the supernovae from all of time. So from all of the galaxies in the universe, all the supernovas provide this diffuse flux of supernova neutrinos. If we look over here, if we look for anti-electron neutrinos, the reactors dominate below about 15 MeV, and atmospherics dominates from about 40 MeV, but this relic supernova spectrum, it depends a bit on the details, gives us, there's a window between the two from 15 to 20 MeV to about 40 MeV where you're dominated by these diffuse supernova neutrinos. Now, the issue with measuring them in a water Cherenkov detector is that you're looking for electrons. And if you have a muon neutrino that interacts and produces a muon below Cherenkov threshold, you don't see the muon, but it still decays and gives you a Michel electron. So this provides the primary background. So you can see this here, and it totally swamps out the signal. Although if you get more statistics, there's a small window from say 15 to 20 MeV where you can maybe see them pull them out. However, if you can start doing neutron tagging, and we think we can do some level of neutron tagging on the protons in Hyper-K, then you will start to reduce this background because the antineutrino interactions should produce a neutron, so you can tag your supernova neutrinos, but the Michel electrons wouldn't have a neutron, don't get tagged. So you suppress this background, and you can then actually start to make a measurement. So you can see here the prospective track of the diffuse supernova neutrino background measurements from super K here from SKGD, where this neutron tag will work very effectively, into and Juno and into Hyper-K, and Hyper-K can really start to pull this down and then collect enough events to make a measurement over the as it runs through the 2030s. The final physics topic that I wanted to touch on was proton decay. So proton decay, of course, was the initial reason that Kamiokande and IMB were built, before they discovered that there were all these strange effects in the neutrinos that were worth measuring. So the question about whether the proton is ultimately stable or whether it decays is a very important one, because it links to grand unified theories. And in grand unified theories, typically there are more massive bosons analogous to the W and the Z that link the quarks and the leptons. And this allows the proton to decay. However, this is suppressed by 1/n⁴, where m would be something in the region of the grand unified scale. So this makes the proton extremely stable. However, the question of whether it's absolutely stable or whether it just has a very, very long lifetime is open and can tell us about these grand unified theories. So the most common interaction modes to look for are the E+π0 mode and the anti-neutrino K+ mode. And these are the two I'll focus on, although there are sensitivity to many, many different modes that can be studied. And you can see here the prospective limits that can be set by various experiments and the impact that Hyper-K can have on these. But I'm actually going to focus in both of these modes on the next two slides. So for the E+π0 mode, what you observe is 3 rings that are electron-like in the detector that have an invariant mass of the proton mass. And so you can limit the invariant mass of these rings to actually find the protons and therefore see the proton decay. And if you look at the invariant mass versus the total momentum that you have, you can see a very nice separation between the proton decay region and the region that's given to you by atmospheric neutrino interactions. And therefore, we can select really quite well these E+π0 events and set limits. So this is what super K is doing, but of course, super K's doubling time is now 25 years to get a factor of 1/√2 in there. So that's going to take a very long time to really further improve the limits. And you can see how Hyper-K catches up in a couple of years and then can push forward with an ultimate sensitivity that's towards 10⁻⁵ years. 10⁻⁵ years is very interesting because it really starts to exclude a lot more grand unified theories and cut down on parameter space significantly. Here, by the way, is the prospective limit for June. This is one of the modes where just more mass wins. And so June isn't really very competitive with even with super K for this particular measurement. Things changed a little bit for K+ neutrino. It's harder to do in a water Cherenkov detector because you don't end up with a nice invariant mass that you can actually measure. What you see is the appearance of a K+ in your detector that you then need to detect. So this can be either through the existence of the muon from the kaon decay, and these are both two-body decays, so you know exactly how much energy the muon would have, and you would end up with a 236 MeV muon. You would always get a Michel electron as well, and you would end up with a 6 MeV gamma ray from the de-excitation of the nucleus that the proton decayed in. Alternatively, you can look for a back-to-back π+π0 of specific energies and pull them out this way. And this allows us to measure this mode as well. However, because we don't observe the kaon directly, there's more competition between the different experiments. You can see here Hyper-K in the red, Juno, which will be very competitive for this particular mode, and June, who can actually see at least a little bit the K+ track perhaps, and so make measurements that are more competitive as well. So you can see here how this is going to be generally a more interesting mode to compare different experiments with. But again, we can reach very, long lifetime limits and really cut into parameter space significantly. So these are some very interesting measurements that will be made in these experiments, and hopefully not just limit setting, of course, but actually measurements of proton decay itself. So just to finish up, here is the overall timeline. The funding was started last year in Japan. So the geological surveys are finished now, basically. The outer yard and the access tunnel are being completed now. The final cavern design is underway, and it's not just the cavern itself, but the utility rooms, the room for the LINAC, all of the full underground laboratory is currently under design, and with a company in Japan that they're doing that, with an aim to start excavation in the cavern next year. That takes about 2 to 3 years to happen, and then the tank gets constructed. That takes about a year, and then PMT installation takes about a year as well, giving us fill with water from the end of 26 and starting operation in 27. In parallel, of course, we have to make the PMTs. Hamamatsu have already started, and the first PMTs have been delivered to Kamioka. We have to start making the cases. We have to start making the electronics and so on. So this is all due to start next year. We have to upgrade the beam. As I said before, the first upgrade happens next year with the power supply upgrades and the near detector facility. The ND280 gets upgraded next year. We will need to start constructing IWCD in about 2025 in order for that to be ready to run in 2027. So I hope I've convinced you that there's a very exciting project due to begin in 2027. There's a growing collaboration of physicists from around the world who are going to be working on this to be the largest detector that we have built, and we'll have a wide program of neutrino oscillation physics. I focus very much on the beam physics today, but as I say, there's a lot more that could be said about supernovas, proton decay, the solar neutrinos, dark matter, and geoneutrinos as well. So hopefully, this is excited you for this program that's coming. So thank you very much for listening.
Thank you very much, Neil, for this very interesting seminar. It was very, very nice. So questions?
Well, I have a couple just
Okay.
maybe start. So on the you mentioned in the beginning about the neutrino interactions and the different regimes. So of course the beam of Hyper-K is different, is geared towards lower energy. But what's the plan of Hyper-K of dealing with the non-quasi-elastic events?
So yeah, there is a higher energy tail. I mean, the off-axis technique cuts it down a lot, but the plan is actually, this is not the right slide to look at. The right slide is IWC. So as I said, what we do is we measure the lepton, and we measure the neutrino energy basically by plugging the lepton momentum that we measure into the CCQE formula. And if everything was perfect, and that applies to CCQE as well, because of course things like Fermi momentum actually change the result and impact it too, then you would end up back with a delta function where you would say, here's my lepton momentum, do this a million times, and this would be the neutrino energies that I get. But life isn't like that. There are many effects that happen. There are these 2p2h interactions of these correlated nucleons where there are multiple protons in the final state. There are higher energy events where you basically bleed down the leptons. So say, you could get a resonant event, but for some reason the pion was absorbed in the nucleus. So it looks like a CC0 pi event, just the same way that the CCQE is. And ultimately, it's actually correct to talk about CC0 pi, CC1 pi, CC2 pi, because CCQE is a nucleon level thing, but it's actually happening inside the nucleus. And if something else happens inside the nucleus, it's just fundamentally not observable. What we can, in theory, observe is what escapes the nucleus, not what's going on inside. So we treat our CC0 pi events like CCQE, but there's a variety of nuclear effects that come into play. So the idea with IWCD is we make measurements, and you can see here there's 3 off-axis angles that have been shown on the plot. but we would use more. And what's been done here in this figure is to add these up in some specific weight to make this narrower Gaussian of neutrino spectrum. So this is narrower than any of these, and we can, and if you change the weights, you can change the energy that you get. And then you add the data together with the same weights, and you can see the lepton spectrum that you get to. So what this type of technique does, and whether this is the right way of doing it or doing it very much like the Tdk approach of here is our model of neutrino interactions, we will constrain it with our near detector fit before we feed it into the far detector fit for the extraction of oscillations. But what this does is it allows us to map much better the link between the lepton momentum and neutrino energy. So we can drive down those systematic effects and understand what's going on and limit ultimately the uncertainty that we have due to all of those effects that are indeed there.
Yep. Thanks.
Any other comments or questions?
You're muted, Nuno.
Nuno, if you are speaking, we are not hearing.
I am sorry, I was muted.
Yeah.
I have a question that is actually related to this, and maybe I've missed. What are your dominant systematic uncertainties for delta CP?
Dominant,
or expected dominant system, because this, in principle, could actually help you reduce quite a bit on those systematics. So I'm quite curious what is limiting you now.
so the dominant systematics, I'm going to be quite loose here because ultimately they're almost certainly going to be interaction uncertainties. And so we can talk about the interaction uncertainties as they exist today in Tdk, where there are various uncertainties due to various different model parameterizations that go on, because the problem that you have is that the neutrino interaction models are still not particularly great. Their nuclear physics and all of this is hard, can't solve things directly, so there are a lot of approximations, and the data is a lot better than the data was 10 years ago from, you know, the data that Tdk has put out, but not just Tdk, also Minerva and Miniboon have put out a lot of data that constrains these models far better than they were. But it's still, I think, a very immature subject in that respect. I mean, the uncertainties are quite large. And sometimes we found in Tdk that, you know, we've learned a lot, we've done better, and our uncertainties have gone up because we learned things of putting more into the models. So what in detail is going to be the dominant systematic here come 2027 is not clear, but I think as our understanding of neutrino interactions improves, they will improve and those uncertainties will improve, but they will still be dominant, I think, for Tdk. You know, for Hyper-K, we want to get down to 1 to 2% uncertainties, then understanding these effects. And the cross-section uncertainties, they don't really come in from the rate, they come in from, you know, understanding this map between the electron momentum and the neutrino energy. And so this technique will help a lot. The upgraded near detector from Tdk will help a lot because of the reduced proton thresholds for the super FTD will allow us to start to look for, you know, in a more detailed way, multi-proton events and looking at things in Tdk at the moment. We had to use vertex activity. So how bright does the vertex look? You know, how much light is at the vertex to try and say whether there are multiple protons, and that's quite hard to calibrate. So it's not been all that useful, though some results have been put together internally. But the super FTD will help us to do that as well. I think the models will mature more as time goes forward. Data from the argon experiments in the short baseline program SBND will have you know, many millions of events, and while they will be best telling people about argon, I think they will help the model development in general. There are a few things that Hyper-K does here that specifically help, one of which, of course, is IWC, the nuclear target is oxygen. And so that helps you get away from uncertainties about going from one nuclear target to the other. The other uncertainty that people have been worried about it's quite amusing for me because I was trying to measure this long before anybody said that we should bother, is this electron neutrino cross section. Because our appearance is in the electron neutrinos and ultimately CP appears in the electron neutrinos, but all neutrino cross sections just about are measured with muon neutrinos. If there are any differences, we need to pin them down. So I think there are 3% uncertainties written down for that right now, based upon some theoretical work that's been done. But ultimately, we would like those uncertainties to be based on measurement, not based upon theory. Because as I said before, these theories include all of these nuclear effects that aren't particularly well understood. And IWCD can also measure measure the ratio of the electron to muon neutrino cross section at the couple of percent level, which again can really help reduce what would be the primary systematics for Hyper-K. We also need to do better on the defector calibration as well. The detector uncertainties as they exist in Super-K are too large for the physics program of Hyper-K. So we are discussing ways we can improve that. Now, statistics for things like pi zeros from atmospheric neutrinos will obviously be much better, but there are measurements that we're making, and there's a big study at the moment about how we can we use MPMTs to understand the detector better, break degeneracies between, say, angular response and absorption, so that we can then feed things in and try and do bottom-up calibrations as well as top-down approaches that we currently use in Super-K. So there's a lot of study going on in order to how to reduce those as well. The beam uncertainties, I think, will still come down too as we learn more about how to use the data from the target tree experiments, NA61 and such. And I think there'll be more data from them with new programs. So we have to improve the systematics everywhere. The cross-section systematics, I think, will still be the most dominant come the time that we're actually taking data. And specifically what parts of that will be dominant in 27, I couldn't say. But this is why a wide global program of measurements is so important. And even potentially things like Newstorm can really make a big difference to the long baseline program.
Okay, thank you. That's
Ruben?
Hi. This is a very ambitious project, so I was wondering, what is its estimated cost and what is the funding model that you're using?
Okay, so the cost is, I can't remember the exact number. I think it's about, it's estimated to be about $600 million project. It depends a little bit on how you specify the funding model that you want to use. The project is approved in Japan, and Japan will deliver the cavity and the tank and the PMT support structure, 20,000 box and line PMTs, various bits of the water system and such. In addition, they will deliver the infrastructure for IWCD and the beam upgrades. Everything else is international contributions. So the UK plans to deliver the outer detector sensors, the MPMTs. There are a number of countries, including Canada, France, and Italy, and Poland, who are aiming to deliver the MPMTs. DAQ will be provided by the UK. The IWCD is primarily a Canadian deliverable. There are a number of groups across Europe and the US who are delivering the ND280 upgrade, although that's a Tdk project. And so it's still coming together in terms of the international contributions. You can only really go to your funding agency and say, give me money to pay for part of this project in this other country when the other country says they're going to pay for it. So the way the model works is the Japanese say, we will fund these bits, which give you this baseline program, and then we want to come in and give you all the bits you need to make it, a real program. So yeah, I think we will understand the international funding context better towards the end of this year when the various different grants go through the various different peer review processes and discuss with the funding agencies in those countries. I'm aware of at least 2 or 3 of the grants that are already with the funding agencies and discussions are going on, but I haven't seen the latest for all of the countries yet. Yeah, so that's basically the model.
Okay, thanks a lot.
Thank you. Any other comments or questions? Okay. I actually have one. So in your slide 38, when you were talking about the supernova, you said that you had 67% efficiency for the neutron tag. How is that?
Yeah, I don't necessarily think that I think is this is what happens if we have a 67% efficiency.
Okay.
The Super-K has done quite well on tagging from the 2.2 MeV gamma rays from the neutron capture on the proton. So if you can do that, and that requires the water to be clean enough, and it requires your sensitivity to be there. So we have the 20,000 box and line PMTs plus some MPMTs, I think. And we will be able to tag some number of the neutrons. I think knowing exactly what that tag is a little bit unclear to me right now. 67% I think is optimistic. Of course, if Hyper-K adds gadolinium, which would not happen straight away, but the detector is being built such that we can do an upgrade where we add a gadolinium water system and then we put gadolinium in. A 67% neutron tag is relatively straightforward. The current loading of Super-K, which is working extremely well now and is actually taking data for Tdk at the moment, is the loading until we get about 50% capture on gadolinium, which means that we can detect about 60% of neutrons, because you can still detect some of the ones on the protons too. But doubling that loading would, which is still not a lot of gadolinium, although it's a very large volume. So I say not a lot, it's still quite a lot. Would push you towards that 67% quite straightforwardly. But that might be an upgrade. That would be an upgrade rather than the initial project. The initial, as written down, baseline project doesn't have gadolinium. But I suspect it would be the first upgrade that would happen. It wouldn't have to take too long to happen.
Okay, thank you. I see Jose has another question.
Okay, maybe just one a bit more general question. I mean, you've shown that for the proton decay, there's size really matters in and Hyper-K sensitivity is extremely robust. But on the CP violation, on the neutrino oscillation program, I think we're going to see probably a healthy mix of competition and complementarity between Dune and Hyper-K in the next few years, and I think that has served CERN and LHC, for instance, very well. So I think I would like to hear a comment of yours from what aspects do you think in which these two experiments are going to be more complementary for the neutrino oscillation program?
So what I've done in this seminar is I've shown Hyper-K results, because there hasn't really been a good attempt yet to combine the sensitivities together. But they are, as you say, extremely complementary, even more complementary than Tdk and Nova. I think we can demonstrate a little bit of it in a very, very simple way by using that as a comparison. So if we compare this graph, you see these contours of constant changing delta CP, and then there's the separation of the mass hierarchy. The scales on these axes will change for Hyper-K. They will turn from maybe 100 events into thousands of events, and so you can imagine that the error bar on this will shrink accordingly. Whereas if we look at the same plot for Nova, you can see how these bands were very much separated. In June, the baseline is longer, so these bands get even more separated, and that's just the basic combination of measuring a Newey appearance. June, of course, will get a lot of power from measuring the spectrum of Newey appearance as well. So they'll get more sensitivity than you would naively get from the June equivalent plot here. But ultimately, I think the complementarity will be ideal. If you were to say, I need to do 2 experiments to measure this, you would do exactly what the world is doing, which is to build one shorter baseline one, which is going to have very, very good statistics, but will have the issue with the mass hierarchy confusing things. And another one, which might be with a longer baseline, so you have to measure the spectrum, which requires a different detector choice, and therefore less mass. but separates the mass hierarchy and gives you, the spectrum to really be what, allows you to measure delta. And that combination is the thing that will give us the confidence in the results, even more so, than Hyper-K or June turning around and saying one of these is 5 sigma. Seeing agreement between these two, looking at the same effect within different technologies with different baselines, I think will be what gives us that. And ultimately, if we want to start mapping the PMNS matrix, we're going to need these different these different measurement techniques, measuring things in different ways, in order to really start to answer questions about, unitarity in that matrix or something else, which I think are the questions that maybe even a little bit beyond what these 2 experiments are doing, at least in their first phase, where it's still, is delta, 0 or pi, or is it something else? But ultimately, those are the questions that as a community, I think we want to answer, and having both experiments run on very similar timescales with not all that different sensitivities, I think is really important for us.
Thanks.
Thank you. We have time for one last question. Nuno?
Yes, okay. So I also have a generic question, maybe a bit unexpected. But so you mentioned that some of your measurements are going to be limited by lack of knowledge and uncertainty in the modeling and of the nuclear interactions and cross sections and so on. And my question is, so there's going to be there are some projects that are being proposed at the LHE to measure neutrinos at the LHE in colliders, and whether this could help in any way to constrain those uncertainties. I mean, of course, I'm suspecting that the energy range is quite different, but I was just wondering.
Yeah, I think the issue with using neutrinos from the LHC is that they're going to be all in the DIS region. And so for June, that might be interesting because the DIS regime is more important for June than it is for Hyper-K. But they are probably not probing the bits of uncertainty that we need to probe in order to drive our systematics down. The CERN program that does really answer these questions extremely well, if it moves forward, is NuStorm. If NuStorm happens, which is an idea to make a muon storage ring, which would have neutrinos coming out from about 300-400 MeV up to about 5 GeV, if I remember correctly, and then to build detectors to measure cross sections. That's exactly the type of program that we need, and the uncertainty on the flux would be tiny compared to that we get from the conventional beams, so that you would really be able to measure the cross sections to the level of precision that we would need. So I think if we're looking at CERN programs for doing that, I think it's this proposed NuStorm program that would be what we need. Now, that wouldn't start before we start running. However, it is more likely that it could be up and running at the point when we really need those systematics to be driven down, because we've collected the statistics in Hyper-K and in June to start being systematically limited.
Okay, and thank you very much again, Neil, for this very, very interesting seminar. And yeah, bye everyone, and have an happy Easter.
Thank you for having me, and happy Easter for everyone.